Hello, can you hear me?
Yeah, sir.
What have you done since the last class?
I read through the chapter.
Are you understanding what is happening?
Yeah,
Like
the dipole part that was a little bit confusing.
before that, field and potential in different cases and all.
Yeah, because that was very similar to the gravitation.
So all of the cases of field and potential should be clear, right?
Right,
Basically, E calculations and V calculations. The general rule is E is KQ by R square in the R unit vector direction, and V is scalar KQ by R due
right,
to a source charge. And now, obviously, we can take many different situations, ring on an axis here. The charge is q and the radius is capital R for the ring. Distance is x. This type of situation, then disk, then line charge, then line charge on perpendicular bisector, right?
right.
Then you have all the spherical shell, solid sphere, spherical shell, and solid sphere situations.
Will they all have like the same formula, but like you swap the variables?
Yeah,
Okay,
everything will be the same except you swap the k for minus g and k for g and q for n. Basically, everything will be same after that.
right,
So if there is a spherical shell outside points, it will behave like a point charge, right?
right,
Field here will be potential here will be kq by r. Field here will be kq by r square. The
right,
distance is r. And for inside points, it is important to realize that field is zero side, but potential is constant, kq by capital R.
right.
You remember that was what was happening in gravitation also.
Yeah,
Sure, no?
yeah,
Similarly, same derivation, everything is same. For solid sphere, also for outside points, it is obvious kq by small r, kq by small r square. For inside points, it is more complicated. The field is easier to remember. Field is as if due to the inner sphere.
right,
So it will be kq small r by capital R cube.
right,
This is the field. The potential is the formula which is slightly complicated in this case because potential has to be due to inner part also and outer shells also.
right. Yeah,
So um, it is something like kq by 2 rq 3 smaller 3 capital R square minus small r square, something like this, right? Right,
yeah,
yes. This is the potential. How do I remember this? Because I remember that the potential at the center should be 3kq by 2 capital R
right.
at center.
Yeah,
When small r is 0, it should work out to be this.
right, right. Yeah.
That's how you have to remember, or whatever way you have to remember, but you have to remember.
All right. Yeah,
The derivations we have done in the previous classes, so you can go back to HCV and see how the derivation is done.
right,
So all of these field potential cases are done in a similar way. The next thing that is important is basically the connection between V and E, which we have also discussed earlier, but we'll revisit that here. dV is equal to minus E dot dr, right?
right,
The point is, why is this connection coming? Because delta V was defined as delta U by Q, right?
right,
Delta U is negative of work done by electric force divided by Q, right?
right,
That is negative of force electric dot dr and divided by the charge q. Force electric is qe dot dr. divided by charge q, so this goes away. So it is negative of integral of E dot dr.
Right.
This is the change in potential when you go from some point to some point. So R initial to R final. This
Right.
will be V final minus V initial is equal to negative of R initial to R final E dot dr. Right?
Right.
This is the integral version. The differential version would be this can be written as integral from R initial to R final dV is equal to negative of R initial to R final E dot dr. And therefore you can say that dV is minus E dot dr.
Right.
Now, what is the significance? This is very important. The significance is if you move around from 2 points, let's say this is the origin, this is your R initial, and this is your R final. If you move a charge from some point here to a point here, obviously there is a change in potential and all, right?
Yeah.
Potential might change in this whole path. Potential here might be different from potential there. V initial, V final. We want to
Yeah.
keep track of how much change in potential happened, right?
Right.
So that can be calculated. Potential is obviously connected to potential energy, and this will be connected to the work done in moving the charge by electric force, right?
Right.
But work done, if you want to calculate, you need to keep track of the electric field at each location as you move a distance dr, right?
Right. Yeah.
But electric field may not be constant everywhere, right?
Yeah.
If it's a long path, you are not sure what is the electric field at that region and so on, right?
Right.
So what we are saying is that you will break up the paths into small dr segments. And you will say in each small dr segment, what is the change in potential happening here? That is minus E dot dr,
Right.
right?
Yeah.
So the change in potential from this point to this point is minus E dot dr, where E is the E at this point. Because it's a small path, we can say that E is constant over the small path.
Right.
But when you have to find the total change in potential, obviously we can't say that it's constant throughout field. Therefore, we have to integrate this dV.
Right.
Are you understanding?
Yeah.
So if you go around, all the small dVs will add up to a total delta V.
Right.
So that is the meaning of this relation. The application of this relation is that it connects field to potential, and we know from our experience with integration and all that calculating potential is significantly easier than calculating field
Yeah.
because it's a scalar quantity. We don't have to worry about direction, so integrations are also easier if you have to find potential.
Right.
So if you are able to find potential properly, then you can use this result to get the field indirectly,
Right.
right?
Yeah.
So if there is a charge distribution, and due to that charge distribution, you need to find potential field at a point. Let's say there's a random charge distribution. Some charges are here and so on. And due to that, you want to find field here. Instead of doing the vector stuff, where you have to add all the field vectors and all, if you can calculate V somehow, we can use the relation to from V we can get E,
Right.
right?
Yeah.
So that is what the whole thing is used for. Obviously, it's interchangeable. You can do both sides. From E, you can get the change in potential also, which we said what we did, right?
Right.
The reverse part is also true. So what we can say is if dV is equal to minus E dot dr, think of this as a small path. This is your R vector. This is your R plus dr vector. Now R vector was, this is the origin. The R vector can be thought of as some point xyz in space, right?
Right.
And this point is x plus dx, y plus dy, z plus dz in space.
Right.
This is P, this is Q. What we want to say, this relation is telling us that VQ minus VP is equal to minus E dot dr, where E is the electric field in this region. It's a small region, so it is constant electric field.
Right.
Electric field could be in any direction, I don't know, right?
Yeah. Yeah.
Now, think of this, because this is your dr vector, you can easily say that the dr vector can be written as dx I cap plus dy j cap plus dz k cap, right?
Right. Yeah.
Because the dr vector is the difference between this vector and this vector.
Right.
This vector is x plus dx I cap, y plus dy z j cap, z plus dz k cap minus this one. That will be your dr.
Right.
And the E, in general, the E which was unknown field can be written as Ex I cap plus Ey j cap plus Ez k cap.
Right. Yeah.
This is the E at point P, which we are assuming will be the same at point Q because they are very close to each other, right?
Right.
So when you write this result, when you take dot product, you are getting minus Ex dx minus Ey dy minus Ez dz. Dot product of these two vectors
Right.
is
Yeah.
equal to the dv, right?
Right.
So the change in potential that happens from here to here is equal to the negative Ex dx, negative Ey dy, negative Ez dz, right?
Right.
Now, what is the benefit of writing it like this? Now, what we can say is, let's say I moved in a specific way, not in an arbitrary way where I moved and changed everything, right? I can move in a way that I go from P to P dash where only X changes.
Right.
Do you understand what I'm saying?
Yeah.
Suppose I moved like this, then the dr vector is simply dx I cap, right?
Yeah.
So in that case, there is no dy and there is no dz. Both are zero.
Right.
Right?
Yeah.
So in that case, the change in potential from P to P dash would be minus Ex dx, right?
Right.
Therefore, Ex is equal to minus dV by dx in that case.
Right.
When dy and dz are zero, right?
Yeah.
Dy and dz are zero means y and z are constant.
Yeah.
So if y and z are being kept as constant and I'm doing differentiation of v with respect to x, that is known as a partial derivative of v with respect to x.
Right. Yeah.
Because in general, potential at different points will depend on all three coordinates, right?
Yeah.
Like in general, potential could be a function of three variables, x, y, z.
Right.
But you don't know how to do derivative of three variable functions, right?
Yeah.
What we are doing is, if potential function was given, we can move in a specific way, only changing x while keeping y and z constant. And in that case, we are getting this result, right?
Right.
And from there, we can figure out Ex as minus dv by dx, where this derivative is the derivative of the potential function while keeping y and z constant.
Right. Yeah.
And it's a derivative with respect to x only. Only one variable you are differentiating and you are treating the other two as constant, right?
Right.
Basically, this gives us the meaning that Ex is basically minus partial derivative of v with respect to x. Similarly, Ey will be minus partial derivative of v with respect to y, and Ez will be minus partial derivative of v with respect to z. Here, y and z are constant. Here, x and z are constant. And here, x and y are constant, right?
Right.
And what I mean is that each time you will move, for example, here you would move from P to a point here, P double dash, which is x comma y plus dy comma z. This was x, y, z, right?
Right.
What has changed? You are only changing the y, right? So
Yeah.
dr vector is dy j cap, right?
Right.
And dv is equal to minus e dot dr. When you do dot product with the general e, only thing that will be left is minus ey dy, right?
Right.
From which we get this. I hope you are understanding.
Yeah.
1 second, hold on. Okay. Are you understanding what I have said so far?
Yeah.
So all you need is basically V as a function of x, y, z. If somebody gives you that, then you can find electric field now,
Yeah.
because it will be this, right?
Right.
Okay. So now we are going to use this method to find or understand a dipole concept, electric dipole. So the whole derivation is basically a practice of what we have just now learned. So what is a dipole? It is like two charges, equal and opposite charges separated by a distance, right?
Right.
This distance is usually small, a distance, and these two charges are separated by some distance, and that whole system is called an electric dipole, right?
Right.
Why are electric dipoles important? Why are we studying it?
Um, I guess because they're used in like many applications,
What applications?
like in many electrical appliances and stuff.
Not really, not electrical appliances. There is far bigger applications which you have already encountered in 11th grade. You have already seen. You're just not realizing.
In chemistry, we had, yeah.
All of chemistry is basically dipole. There are so many covalent forces, polar covalent bonds. Everything is a dipole.
Right.
So many molecules. Water's properties are because water is behaving like a dipole.
Right. Yeah.
So there is a tiny negative, tiny positive, tiny positive. These equal and opposite charges are dipoles basically.
Right.
So many properties of water depend on the fact that there is a tiny dipole here, right?
Right.
It will come so many times in chemistry, a dipole. You understand what I'm saying?
Yeah.
So basically, it comes so many times in chemistry that small charges are separated by a small distance. That this system we are studying separately because it is so important. And what we are going to say is we want to predict how a dipole affects the space around it. Obviously, the way it can affect the space around it is by creating a field and some potential at some point. Right?
Right.
That's how any charge will affect any space. It can create field and potential, right?
Right.
So our job right now is to predict what is the field and potential at a random point near a dipole. And the way in which we set up the whole system is we take the negative and positive charges here, we take the midpoint or center of the dipole as our origin. And from here we draw the r vector, which is the vector to the point P. And let's say the r vector makes angle theta, theta with the axis of the dipole. This line is the axis of the dipole.
Right.
Axis of the dipole is the line joining the two charges, right?
Right.
Now, the separation between them was A. This is the r vector from the origin, which is the center of the dipole, to the point P. And our job is to find the field and potential at this point P, right?
Right.
Now, in all of these situations, usually in real life situations, the dipole size is really small compared to the distance at which we want to study its effect. You understand what I mean?
Yeah.
The size of the dipole A is much smaller than this length R, usually.
Right. Right.
So we will be using approximations based on that fact. But first our job is, we will not try to find field first because field will be complicated due to the vector nature of it.
Yeah.
We'll first find the potential, and potential is a scalar, so we just need the distance to this point and the distance to this point, right?
Right.
Let's call this R1, let's call this R2, right?
Right.
So potential at the point P should be KQ by R1 minus KQ by R2, right?
Right. Yeah.
But I don't want to use new variables. I want to write R1 and R2 in terms of this middle length, which was R, right?
Right.
I want only a single a distance vector or distance, right?
Right.
I don't want multiple variables for that.
Yeah.
So what I will do is I will use an approximation and I will say drop a perpendicular like this and extend this line a little bit and drop a perpendicular like this. Okay.
Okay.
Now think about it. If the distance is really small and the point is really far, and you have joined all of this and all like this, right?
Right.
You should realize that if you label this point as P or P dash and this point as P and this point was O, like, and this is A, you can say that AP is roughly same as PP dash, right?
Yeah.
Because the triangle is so narrow, right? It's almost
Right.
like an isosceles triangle only.
Right. Yeah.
Only works if it is a if this approximation is true. Right?
Right.
Doesn't work if the distance is really small and then obviously the distance lengths are different. Right?
By that same logic, can't I just say that PO is also equal to PA, roughly?
PO is, but then if you say that, then there is no purpose to the whole thing. You'll get zero.
Yeah.
If you say that this length is roughly same as this and roughly same as this, then nothing will come. No,
Right. Yeah.
you have to do an approximation that gives you something valuable.
Right. Right.
Right? That is an approximation that destroys the whole thing. Right?
Right.
So what we will say is that this length is roughly same as this much,
Right.
and we'll say this big length R2 is roughly same as till here.
Right.
So then there is a difference between the lengths, no?
Yeah.
Now we just have to find this length. So what we can say is, see, the overall distance between the dipoles was A, so the distance between this much is A by 2, and we can easily see that this is A by 2 cos theta, right?
Yeah.
So we can say R1 is equal to R minus A by 2 cos theta.
Right. Yeah.
And similarly, this is A by 2 and this is theta, so this is also A by 2 cos theta. So we can say R2 is equal to R plus A by 2 cos theta.
Right.
So now you put that in this formula, you get KQ by R minus A by 2 cos theta minus KQ by R plus A by 2 cos theta,
Right.
right?
Yeah.
And we get B is equal to KQ. And now say KQ is common, and when you simplify, it is A by 2 cos theta plus A by 2. So A cos theta by R square minus A square by 4 cos square theta, right?
Right.
Now think about it. Anyway, A was less than R. So A square is much less than R square, right?
Right.
And A square by 4 cos square theta is even smaller, right?
Right. Yeah.
So I can totally ignore this part here
Right.
compared to R square, right?
Right.
So I'm getting V is equal to KQ A cos theta by R square, right?
Right.
This is my first result. I have found the potential at this point. The only things that are used here are r and theta, where r denotes the distance of the point from the center of the dipole, and theta is the angle that the r vector makes with the axis of the dipole, right?
Right.
Do you understand how we got this?
Yeah.
Now we have to use this to figure out the field, right? We'll basically use this expression that we have gotten for potential to figure out the field. You understand what I'm saying?
Yeah.
This is theta. This whole thing was A. And I know potential at P is KQA cos theta by R square. Right?
Right.
What I don't know is what is the field at this location. Right?
Right.
So I will define two vectors, just like remember in circular motion we had defined a radial and a tangential vector, right?
Right.
I will define one vector like this, which is your ER vector, and one vector like this, which will be called our E theta vector, right?
Yeah.
these are two perpendicular vectors. Obviously, if the point P has changed and point P was somewhere here, the ER would be like this and the E theta would be like this, right?
Right.
You understand that ER and E theta depend on the location of the point P, right?
Yeah.
Okay, so why am I defining these two perpendicular vectors? Because I will say that the field at this point in general is like this, right? Let's say.
Okay.
I don't know what it is, but
Okay.
it will have components in two perpendicular directions, right?
Yeah.
It could be split into two components, one along the radial line, one along the perpendicular to the radial line, right?
Yeah.
Okay. Our job is to find the two components. If we can find both of these components, I know the full field, right?
Right. Yeah.
Okay. So just like in the earlier case, if you remember, when we did, when we used this, we said that I can move in a specific direction. Here dr was dx I cap, dy j cap, dz k cap. And if you move in only one of the directions, x, then you will get the ex, right?
Right.
So now here are two components, er and e theta. So I will move in two separate directions. One direction is the direction of r, one direction is the direction of this, right?
Right.
So now I will do this analysis. Like, let's say this is my point P and this was the R and this was angle theta. I move from P to another point P dash, right?
Right.
P dash is at R plus dr and the same angle theta, right?
Yeah.
So the dr vector for me is simply dr er, right?
Right.
You understand?
Yeah.
So the change in potential from here to here, dv, should be minus E dot dr vector. But when you do the dot product with this particular dr vector, it will be minus er dr, right?
Right.
You understand?
Yeah.
Because my displacement vector is dr times er vector, right?
Right.
And E vector was this. So when
Yeah.
you do dot product, there is no theta component. So it's only going to give me this much, right?
Right.
And here we are assuming mentally that theta is constant.
Right.
So er is simply minus partial derivative of b with respect to r, right?
Yeah.
Correct?
Yeah.
So now we look at this formula and do a partial derivative of this formula with respect to r, keeping theta constant, right?
Right.
So kqa cos theta is all constant, and we have to differentiate 1 by r square, which will be minus 2 by r cubed, and there is a negative sign ahead. So it will be this way.
Right.
Er is coming as 2q kqa cos theta by r cubed.
Right.
I hope you are understanding how we got this.
Yeah.
Okay, so one component of the field we already found, right?
Right.
Now we will do the other component of the field. Again, the figure is same. These are my charges, minus q cube. This is theta. But now you have to realize that you have to move in a different way. You have to move to a point somewhere here
Right.
along the e theta direction, right?
Yeah.
Now think about it. I want to keep my r constant now, right?
Right. Yeah.
You just rotate it by some distance, and this is your location. But now this is theta plus d theta, right?
Right.
So think about it. This small distance should be roughly r times d theta, right?
Yeah. Yeah.
Because this angle is d theta,
Yeah.
and the radius in which you have rotated is r.
Right.
So my displacement vector is actually 0 er plus 0 er plus r d theta e theta, right?
Right.
R d theta is the actual distance you have to move, right?
Right.
E theta is the direction. And my electric field in general was ER R plus E theta E theta. So dV is minus E dot dr, and therefore you get minus E theta r d theta, right?
Right.
Correct?
Yeah.
But when you have moved like this, what has been kept constant? R is constant, right?
Right.
You have not changed your radius, right? You have only
Yeah.
changed angle. So
Yeah.
when now we say E theta, we can say it is minus dou V by dou theta and 1 by R, right?
Right.
This is a partial derivative of V with respect to theta, keeping R as constant.
Right.
And V was KQA cos theta by R square. So dou V by dou theta would be KQA by R square is constant. Cos theta is minus sin theta, right?
Right.
And when you do minus 1 by R dou V by dou theta, it becomes KQA sin theta by R cube, right?
Right.
So this is the component in the theta direction. We have already found the component in the uh, ER direction. So you are getting overall is going to be 2KQA cos theta by R cube ER plus KQA sin theta by R cube E theta, right?
Right.
And V was KQA cos theta by R cube, right? No,
Right.
not R cube, R square,
Uh,
correct?
yeah. Yeah.
And the setup of the problem was like this. This was the R, this was the theta, these were the charges, the distance between them was A, this was the point P,
Right.
and this is E at P and V at P, right?
Right.
And the only approximation is that A is less than R,
Right.
correct?
Yeah.
Now look at this field. This field is telling us two components, one along this, right?
Right.
This is your ER, this is your E theta. So net field is something like this, right?
Right.
E resultant vector's magnitude would be square root of ER square plus E theta square, right?
Yeah.
Because the two components are perpendicular to each other. So this will become basically, you can take KQA by R cube outside and it will be square root of 4 cos square theta plus sin square theta, right?
Right.
So it is 1 plus 3 cos square theta. This is the resultant magnitude of the electric field at this point, right?
Right.
Are you understanding what I'm saying?
Yeah.
The direction of this electric field is obviously not in the same direction as the theta and all, because
Yeah.
it is a resultant of ER and E theta, right?
Right.
So if your direction of the R vector was like this, your field vector is like this. There is a particular angle between the resultant field and the R vector, ER vector, right?
Right. Yeah.
That angle can be calculated. You can say tan alpha is equal to E theta by ER, right?
Yeah.
And E theta by ER, when you do, you'll get tan theta by 2, right?
Right. Yeah.
So the angle here alpha is such that tan alpha is equal to this angle theta's tan by 2,
Right.
right?
Yeah.
And obviously now you can take all sorts of special cases of field and potential. This is the field formula and this is your potential formula. The typical cases that you will encounter are when the point that you have to analyze is on the axis of the dipole or when it is on the midpoint or perpendicular bisector of the dipole. Those are usually asked many times, those type of situations are given. So maybe point is somewhere here on the axis of the dipole, right?
Right.
This is my center 0, 0. Obviously, now this is my R vector. ER is like this. E theta is like this, right?
Right.
Technically here theta is 0, right?
Yeah.
So potential is KQA cos theta by R square. So potential is easy. KQA cos theta is 0. So KQA by R square, right?
Right.
Where R is this distance from O to P,
Right.
right?
Yeah.
But field, if you see, field will, one of the components of the field will vanish. So on the first component, you had 2kqa cos theta by r square, rq,
Yeah.
uh, for the first component. So that component remains, right?
Yeah.
Because cos theta is 1. The
Right.
second component was kqa sin theta by rq. That component vanishes, right?
Right.
So there is no e theta component there,
Right. Yeah.
which makes sense also. The field cannot be vertical, no? There cannot be any component vertical.
Right.
If you just did normal calculation of field due to negative q would be like this and positive q will be like this, and you have to, the entire field should be horizontal, right?
Right.
Which is what we are getting from the formulas also, correct?
Yeah.
This position of point P is usually called the axial position. There is another position that is sometimes asked, which is the equatorial position, which is somewhere here, right?
Right.
Which is a point that is on the perpendicular bisector, right?
Right.
So theta is equal to 90 degree. And now the first component, cos theta component vanishes for the field, right?
Right. Yeah.
2kqa cos theta by rq, so that is 0. And kqa sin theta is kqa by rq e theta, right?
Right.
Er is, there is no field in this direction, but there is field in this direction.
Right.
Are you understanding what I'm saying?
Yeah.
And notice that potential at any point on this line is going to be 0 because cos 90 is 0.
Right.
Why? Because since the point is on the perpendicular bisector, obviously these distances are equal, right?
Right.
And the charges are equal and opposite, so potential has to be 0.
Right. Yeah.
I hope you are understanding.
Yeah.
Okay, so that is your basic results, kqa cos theta by r square. Now we will look at one more thing. 2kqa cos theta by r cube r plus kqa sin theta by r cube d theta. Now, what I want to say here is one more thing. There is a term called dipole moment vector that is defined sometimes. Okay, so dipole moment vector. It's a vector that is defined, and it's the vector from minus q to plus q.
Right.
Minus q to plus q, that is the direction of the vector. And what is the magnitude of the vector? Magnitude of the vector is always defined to be the charge times the distance between the two charges.
Okay.
So in this case, my dipole moment vector, or let's call it T vector is basically QA I cap, right?
Right.
Why? Because the direction of the dipole moment is from minus q to plus q, which is I cap here.
Right.
If it was some other direction, I would have to write the dipole moment vector also in terms of its components.
Right.
Correct?
Yeah.
Why are we talking about this vector right now? The magnitude of the vector is always q times a. The direction is determined by the minus q and plus q.
Right.
Because we are talking about this because that helps us simplify or see connections in the formulas a little bit. This point was p, this was r vector, and this was theta, right?
Right.
Now notice that the dipole moment vector is like this p, right?
Yeah.
And p was equal to qa in the, actually this direction is the I cap here, right?
Yeah.
So if you think about it, here qa is already there, no?
Yeah.
qa is already there. Let's multiply an r on top, cos theta by r cube, right?
Right.
Can you see that the dot product of r dot dipole moment vector would be
Right.
what? It would be r and qa cos theta, right?
Yeah.
Because the r vector is like this, dipole moment vector is like this, the angle between them is theta.
Yeah.
So r dot p is rqa cos theta.
Yeah.
That's why I multiplied by r and made it r cube here. Because now I can write the top part as k R dot P by R cube,
Right.
which is a simpler formula.
Yeah.
If you know your dipole moment vector and you know the position vector of the point where you are trying to find potential, right?
Right.
You just take that position vector and the dipole moment vector K R dot P by R cube,
Right.
right?
Yeah.
This is a formula that you should be familiar with because later in magnetism also we'll see similar things. So right now you should not be like ignore this and all. Just because you remember this version doesn't mean you can ignore the other version here. Okay?
Right.
The way it is coming is just basic maths and how we have defined a dipole moment vector, right?
Right.
On the other hand, for the potential, for the field, here also you can say things like that, but it is a little more complicated. It is, see here, if you multiply 2kqar cos theta by r power 4, okay?
Yeah.
And here kqar sin theta by r power 4 e theta, right?
Yeah.
So notice that this is a dot product of r and p, right?
Yeah.
And this is a cross product of r and p.
Yeah.
But here you have cross product, but you have to do mod of the cross product technique.
Right.
You are
Yeah.
not writing the cross product as a vector, you're taking the magnitude of the cross product.
Yeah.
You can say it is 2k p dot r by r power 4 r plus k p cross r mod of that by r power 4 e theta, right?
Right.
Do you understand why I have put a mod?
Yeah.
The magnitude of the cross product is qar sin theta, right?
Right.
I hope you are getting what I'm saying.
Yeah.
So those are alternative ways to see the same dipole results. Then there are some basic, very easy stuff. If you understand this much, you can easily explain why if you place a dipole in an electric field, there will be a torque on it, right?
Right. Yeah.
That is obvious because if there is an electric field like this, obviously the force on this dipole is like this
Right.
QE, right?
Yeah.
The force on this end is minus QE,
Right.
correct?
Yeah.
So about the origin, if this distance is A, this is 0, 0, and you can say that this much is A by 2. And let's say this angle is theta, right?
Right.
Do you understand what I'm saying?
Yeah.
The dipole, the dipole moment is going to be from this in this direction. This is the P vector, and that vector is making theta with the horizontal,
Right.
right?
Yeah.
So the torque about this O due to this force would be this R cross F, right?
Right.
Which E by 2 cos theta I cap plus A by 2 sin theta J cap cross product with QE I cap, correct?
Yeah.
I hope you are understanding what I'm saying.
Yeah.
I cross I is 0, J cross I is minus K because the rotation is clockwise. By right hand thumb rule, the rotation direction will be minus K, right?
Right.
So this cross this you get QE A by 2 sin theta, correct?
Yeah.
And then similarly, now the R vector is like this. Now the R vector would be minus A by 2 cos theta I cap minus A by 2 cos theta J sin theta J cap.
Yeah.
It's the same, but now the reverse direction.
Right. Yeah.
Torque here would be minus QE I cap being cross product with this stuff. Minus A by 2 cos theta I cap minus A by 2 sin theta J cap. Doing cross product with this. I cross I again gets becomes 0 and you get QE A by 2 sin theta Minus minus becomes plus, but J cross I is minus K, right?
Yeah. Yeah.
So notice that both the torques are adding their effects, no?
Yeah.
So the total torque is what? Q E A sine theta, right?
Right.
Are you understanding?
Yeah.
And now see that this is technically P cross E, where
Right. Yeah.
P vector was this vector, no?
Yeah.
P vector was this vector, which was making an angle theta with the electric field, right?
Yeah.
So P cross E is this, no?
Right.
So we can say that if the dipole is placed in an electric field, the total torque on it is P cross E, where P is the dipole moment vector and E is the electric field.
Right.
Similarly, the last part is deriving potential energy of a dipole, and it comes out to be minus P dot E.
Right.
If a dipole is placed in a electric field, obviously it will see in a random situation. If you had placed it was experiencing torque, right?
Yeah.
It wants to turn around and get in this situation like this, right?
Yeah.
So that now there is no net torque on it
Right.
because field is like this, right?
Yeah.
So this is your baseline level of the dipole. If it was already like this, it would not turn, right?
Yeah.
But since it is at a different location, a different theta, that time it has more potential energy, right?
Right.
You can call this as your zero potential and call this as your higher potential, right?
Right. Yeah.
So that is what this is coming from. You can define this U as change in U is negative of work done by electric field. So
Right.
if you take the dipole from this position and bring it to this position, this is initial, this is final, right?
Right.
You can say U final minus U initial is negative of the work done by electric field in bringing in doing this rotation, right?
Right. Yeah.
Work done would be torque d theta, right?
Right.
And you will have to calculate this, and you will be able to prove that total U can be defined as minus P dot E.
Right.
Are you understanding what I'm saying?
Yeah.
You need to read that remaining part that is left for dipole and then pay attention to that last page where he talks about conductors, insulators, and electric field inside a conductor.
Right.
The types of bodies like insulators, conductors, and so on, that is important to understand. And also that electric field inside a conductor, the last page section. Okay.
Yeah.
Once you have read that, you need to start doing the exercises, and you should be fairly ahead of when Alan was going to start all this.
Yeah.
We will finish the exercises by next week. We'll go on to Gauss's law and other things.
All right.
Uh, what is happening in your? What happened in your test?
Uh, I think I'll get around 230. It was a simple test.
Physics part was okay.
Yeah, physics was fine. Physics, I think, was the hardest out of the three. Uh,
Hmm.
Physics, I think I'll get around 60 to 70.
It's fine as long as you understand the basics. We will improve it later when we discuss it.
Right.
Make sure that you don't have any conceptual difficulties. Like
Yeah.
your problem solving will come with practice and all, but mainly the concept should be clear at least.
Right.
Okay, fine. That's all for now. Let's start doing the exercises for chapter 29 and read up again whatever sections you have not yet fully read. And we'll discuss the exercises in the next class.
All right.
Fine. See you next time.
Okay. Thank you, sir. Bye.